Hello, thank you for joining us. My name is Ulises,
And I'm Steven.
and today we'll be talking a little bit about pancreatic triacylglycerol lipase. So, a little bit about it is it belongs to a family of enzymes known as lipases, which are secreted in the pancreas. It's naturally found in vertebrates compared to non-invertebrates, and so these examples such as mammals, reptiles, birds, and amphibians. These are all vertebrates that have pancreas, and so this is where that enzyme can be found. It's involved in the catalysis for specifically the hydrolysis of triglycerides, and so therefore is a hydrolase. This is an overview of the reaction that occurs. So it involves a triacylglycerol, and it hydrolyzes it, giving 2 fatty acids and 1 monoglyceride. So that reaction gives off, it involves 2 molecules of water as well as the pancreatic lipase to do this reaction in that step. So the way this mechanism looks is we have a pancreatic lipase and we have molecules of water. So the molecules of water, since this occurs in the body, our molecules of water can act as both an acid and a base, and so our oxygen will be negatively charged of that water molecule, and it will attack the carboxyl carbon from our first fatty acid, pushing off the electrons from the pi bond that form between the oxygen and the carbon onto the oxygen. So now our oxygen is negatively charged, and we now have a hydroxyl group attached to that carbon from our first molecule of water. And so this oxygen wants to reform its pi bond. And so when it does that, it will reform the pi bond, releasing a leaving group. Now our water molecule, or our OH hydroxyl group, can be a good leaving group, but what is instead is the leaving group is our first fatty acid. And so it reforms this the pi bond, and our first fatty acid is released. And so you can see here our first hydroxyl group and our remaining fatty acid. So this is our diacylglycerol. And now another molecule of water attacks this remaining carboxyl carbon. And so what happens, again, our oxygens from the pi bond to the carbon are pushed to the electrons are pushed to the oxygen, making our oxygen negatively charged. We'll have another hydroxyl group onto this carbon, and this pi bond want to reform. So as it reforms, we again need another leaving group, and so that's when our next fatty acid is released, and we have, as you can see here, our 2 hydroxyl groups and our monoglycerol. So again, as what our overview of what just happened is we have, because of our 2 molecules of water in the pancreatic lipase, we get released in one step. We get released the 2 fatty acids and the remaining monoglycerol. So there has been study. Well, after this reaction occurs, what happens to these 2 fatty acids is they move through the small intestine and they meet a protein known as lacteal. Now the lacteal absorbs the fatty acids, and so there has been studies done linking the absorption of these fatty acids with obesity. And so research has been done in trying to treat this obesity, and therefore what researchers have come up with is ways to inhibit this hydrolysis, right? This hydrolase, our pancreatic lipase. It will to inhibit this molecule in order to prevent it from releasing the fatty acids, thereby preventing the absorption of the fatty acids. So such an inhibitor, such as tetrahydrolipstatin or orlistat, allows triglyceride to be released from the body as excrement. So by preventing this hydrolysis, we have just the larger molecule of triacylglycerol is just released to the body as waste. So therefore less fat is absorbed. And so the way this occurs, you can see our inhibitor, another name for the drug name for tetrahydrolipstatin or orlistat is just drug name, in this case it's Xenical, but just imagine that is our orlistat or tetrahydrolipstatin. It inhibits this molecule from doing our lipase from performing its function, and therefore preventing it from doing the hydrolysis. So here's an image of what orlistat looks like, and again you can see that it is preventing, it interacts with the serine, interacts with lipase, and so it will prevent it from doing this hydrolysis as well.
This forms a covalent catalytic bond in serine 152, and it is non-reversible, so the lipase is unable to function after orlistat binds in that active site.
So when researching, this is our what our prediction is for when we did our research is by inhibiting the function of pancreatic lipase will lead to a decrease of fat absorption. And in reading a research article, the research article we read on was the modulation of pancreatic lipase activity by alganates. And Stephen will cover a little bit about what that experiment entailed.
This paper took 23 different alganates, and they used an artificial and a natural substrate to test whether or not these alganates are effective lipase inhibitors. So that's exactly what their hypothesis and objective was trying to say in the paper. Next slide. So the materials and methods were very simple. They had 4 different solutions, and they used different combinations of these solutions in order to test these alganates. Now, first thing we should mention is colipase. That was also in the previous picture showing the mechanism of how lipase with xenocal or orlistat works. This is colipase, and it is an enzyme that helps lipase function. It acts as an anchor, and in one solution they had the colipase with a buffer. In the second solution, they either had DGGR, which is shown right here, or olive oil, and these were the substrates. These were the triglycerols that they wanted to test. And DGGR is just the artificial substrate, and obviously olive oil is the natural substrate. In the next solution, they had pancreatic lipase, and then following that, they had the alganates. And alganates are just sources from seaweed, primarily, but they also used artificial sources of alganates, and that was the 4th solution. Again, there were 23 different types that they used. Now, the first experiment, they tested DGGR, and so they had their one solution of DGGR, and they had solution 1, which contained colipase with some orlistat in certain assays, and then other assays had the alganate solution. And then solution 3, they had the pancreatic lipase. They combined these, and then they combined solution 2 with them in 96 assays. Wells. Now, in the second experiment, they did basically the same thing. This side, they had the olive oil solution with the buffer and the alganates. And then on this side, they simply had just the enzyme solution, colipase and lipase, with orlistat. One thing that this paper didn't talk about was why they performed the 2 experiments slightly differently. Maybe for the effectiveness, but that is unknown from what they talked about and should be mentioned. Now, the results, in order to show that they had anything happen, they used this formula, which I will not say, but their test that they used for the inhibition levels was a 2-way ANOVA. The carbohydrate content versus the inhibition, they used a Spearman test. And the inhibition by alganates from 2 different seaweed species, they used a 1-way ANOVA with the Tukey test. This is the first graph that they showed, and over here we have our absorbance, and this is time for our x-axis. Now this line down here represents orlistat, and as you can see, there was basically almost 100% inhibition of pancreatic lipase when orlistat was present. This big curve is when there is no orlistat or alganate, so it was the control. And this line here shows was the alganate experiments or where alganates were present, and it shows that pancreatic lipase was inhibited similar to how orlistat inhibits pancreatic lipase. Now, these graphs explain the different alganate sources. So here, from this species of seaweed, they had glucuronic acid, and those alganates worked better than the mannuronic acid alganates. And you can see here, as you start from here, going to the right, you have more mannuronic acid alganates. Over here, they also tested the alganates at different concentrations. So these are different alganate sources, or different alganates rather. And the farther left is the lower concentrations, middle is a little bit more concentration, and the right is more concentration of alganates. And as you can see, the more concentrated alganate source they used, the higher percentage of lipase inhibition occurred. Now, that was all for DGGR. This is now for the olive oil experiment. It's a little confusing, and they, again, didn't explain why the graph was presented this way, but it's basically flipped on the x-axis, I guess you can say, from that previous graph. But here is absorbance again, and this is time. This top line shows how orlistat inhibits pancreatic lipase. And this curve here shows the control, and this middle curve shows how alganates inhibit pancreatic lipase. So it worked for the olive oil experiment as well. Again, similar graphs. These were the glucuronic acid alganates from this species of seaweed, and these were primarily the mannuronic acid alganates from the other species. Again, the glucuronic had a higher percent of lipase inhibition than the mannuronic. And then again, they tested the different concentrations, and the higher concentration they had consistently had higher percentage of lipase inhibition. Now, this is showing the p-values, and here you can see F of G, F of GG, F of GGG. So these are the glucuronic acid alganates. They had very high, or very low p-values rather, for DGGR and olive oil, but for these two sources. And you can see some of the seaweeds had oftentimes a mixture of the two, a ratio, if you will. So here you can see Mg or MgM or MgG. So when they had glucuronic acid in them, they inhibited lipase much better than just mannuronic acid. Again, very low p-values in the DGGR experiment and in the olive oil experiment. So overall, this paper stated that depending on the structure, the glucuronic acid or the mannuronic acid of alganates are effective as lipase inhibitors. Now, unfortunately though, the exact inhibition of alganates is, well, the exact mechanism of how alganates inhibit pancreatic lipase is unknown, unlike orlistat. Now, these are considered dietary fibers, and they wanted to mention that there are other dietary fibers that exist other than these. And again, just to solidify what Ulises was talking about earlier, alganates do increase fatty acid excretion. And the paper said that some useful way of using alganates is by adding them to processed foods to lower the intake of fatty acids, or the absorption of fatty acids into humans, and so therefore, again, increasing their excretion.
Mm-hmm. And so when taking like a medication such as orlistat, for example, as I mentioned earlier, you might take these dietary fibers in conjunction because they were all working in conjunction with inhibiting the
Right.
function of lipase.
Right.
And so instead of maybe just focusing on using that medication, you might use something more natural like dietary fiber in order to help out that process a bit.
Right.
So, and here are references, and this concludes our presentation on pancreatic lipase. Thank you for joining us.
Thank you.
And